Welcome back to the class on a power semiconductor trace. In this lecture, we are going to discuss about the pulse width modulation of a three-phase inverter. Initially, we are going to brief about the normal inverter as well as the PWM inverter. This is the circuit diagram for the single-phase inverter. This is the input voltage. This is the capacitor. Generally, we are keeping this capacitor at input side to maintain a constant voltage. S1, S2 control switches, S3, S4 also the control switches. Across the switches, the diode is also there, but for simplicity, we are not represented the diodes in the circuit diagram. Across these two terminals, the single phase induction motor is connected. If the S1, S2 is on, the load voltage becomes a positive. If S3, S4 is on, the load voltage becomes a negative. So in that manner, we are going to control the switches S1, S2 and S3, S4. So the input voltage is converted into the AC voltage that will be applied to the single phase induction. This is the base voltage to the S1, S2. This is the base voltage to the S3, S4. Whenever we are given the base voltage, the switch is on. If we withdraw the base voltage, the switch will be off. So from this point to this point, S1, S2 is on. So the output voltage is equal to the input voltage, that is VD. Again, from this point to this point, S3, S4 is on. So the output voltage becomes a negative. In this manner, a constant DC voltage will be converting into the AC voltage, which is applied to the induction. Here, only one parameter is there to change the RMS output voltage, that is the VD. So we have to change the height of this VD, then it gives the variable RMS voltage. Now we are going to see the PWM inverter. In case of PWM inverter, we have a reference voltage and carrier voltage. Both are given to the comparator or logic circuit. It is comparing the VR and VC, making the output is which is activating the triggering circuit. The triggering circuit will giving the pulses to the S1 to the during the positive cycle of the reference voltage, it will give the pulses to the S1, S2. During the negative cycle of the reference voltage, it will give the pulses to the S3, S4. That is the one condition. Another condition is that depending upon how we have written the logic here, suppose if we write if VR is greater than the VC and the output is 1 means the triggering circuit will be activated. Then it gives the pulses to the S1, S2 or S3, S4 depending upon whether the input voltage is the positive cycle or the negative cycle. Now that we are going to see now. Here we have taken the sinusoidal pulse width modulation. So this we have taken the sine wave as a reference wave. This triangular wave with a carrier wave. Here we have written the logic such a way that if the reference is greater than the carrier, then it will be activating the triggering circuit. During the positive cycle of the reference wave, it is giving the pulses to the S1, S2. During the negative cycle of the input voltage, then it gives the pulses to the S3, S4. So proportionally, here we are getting the positive voltage as well as the negative voltage. This is the VD. Here, what is the difference between this and this waveform? This output voltage is consisting of more number of harmonics, whereas the PWM output voltage consisting a less number of harmonics, which gives the more real power to the induction motor. Now we are going to see the three-phase step wave inverter. The delay angle between any two successive switches is the T/. Once the switch is on, it has to conduct a T/2 seconds. Suppose if you take the frequency is a 50 Hz, then T becomes a 1/50, that is equal to 0.02 seconds. The delay angle between the successive device is the 0.02 divided by the 6. This is the delay. This many seconds. Next, once the device is on, it has to conduct this much of time, nothing but a 0.02 divided by 2, which gives the 0.01 seconds. In this manner, if we on the switches, it will give the frequency of 50 Hz. This is the line voltage of a stepped wave inverter. From 0 to pi, the voltage is Vd. From pi to 2 pi, this is the waveform output voltage, that is minus Vd. If you write the Fourier series for this output voltage, VAB equal to 2 root 3 Vd by pi sin omega t minus 1 by 5 sin 5 omega t minus 1 by 7 sin 7 omega t plus 1 by 11 sin 11 omega t plus 1 by 13 sin 13 omega t, so on. This waveform is symmetrical about the x-axis, so it does not consisting a even number of harmonics, consisting only the odd harmonics. That we can see in the Fourier series. If we write the Fourier series for the phase voltage, so this voltage divided by the root 3. So we are getting the 2 Vd by pi sin omega t. Same series we can see here also, but only thing is this magnitude will be reduced by root. This is the fundamental component. Remaining all components are the harmonic components. Fifth harmonic, seventh harmonic, 11th harmonic, 13th harmonic. Due to the fundamental component only, there is a torque will be developed in induction motor. Remaining harmonic component will simply creating a heat in the induction motor, which gives the more losses in induction motor. The efficiency of the induction motor also will be reduced. Fundamental voltage of phase voltage, that is equal to root 2 by pi Vd. See, previously we have seen here, this is the maximum voltage of the fundamental divided by root 2, we are getting the VAN equal to root 2 by pi Vd. This voltage only contributing the torque developed in a induction motor. Now we have seen how to control the output frequency. Because we have taken the f equal to 50, so the t value becomes 0.02. Suppose if you take the f equal 25, then t value becomes a 0.04. Suppose if you want the output frequency is 100 Hz, then t becomes a 0.001. Like that, by changing the value of the t for a given value of the frequency, we can control the frequency of the inverter given to the induction motor. But how we are going to control the RMS voltage? Because in V by F control, we can able to control both voltage as well as the frequency. So this is the RMS output voltage. It is a function of a VD. Unless until if you are not controlling the magnitude of the DC voltage, we can't control the RMS output voltage. Suppose if the DC voltage is available practically, then you have to use the chopper circuit to get the variable DC voltage here. This is a high LC filter. The main function of this filter is that it reduces the ripples in output voltage and current also. Moreover, the operation of this inverter is independent of the chopper. These are the two functions of this filter. Now, by means of this chopper, it is given a variable DC voltage so that this inverter will give the variable RMS voltage. Suppose if the available supply is the AC supply, then you have to use the control rectifier circuit, which gives the variable DC voltage at this capacitor. This inverter will give the variable RMS voltage to the induction. Already we have seen how to control the frequency of an AC voltage given by the inverter. The main drawback of stepped wave inverter is that the output voltage is consisting of low frequency harmonic. Because of low frequency harmonic, losses in a machine will be increases, which decrease the efficiency of the motor develops a pulsating torque due to the fifth and seventh, 11th, and the 13th harmonic, which create a jerk in a motion of a motor at a low speed. Harmonic content in a motor current will increases at low speeds. Suppose if you want to run the motor at low speeds, you have to apply the less voltage as well as frequency also will be lesser. So the harmonics in a motor current will be more. The harmonics in a motor current will be increases at low speed. The machine saturates at a low speed due to the high V by F ratio. These two effects overheat the machine at a low speed. Thus, limiting the speed of induction motor is to 40% of the base. So it is giving a limitation to the how much minimum speed is required to the induction motor if it is driven by the stepped wave three-phase pulse width modulation inverter. Already we have seen in the single phase pulse width modulation the same circuit. Only thing is we are going to control the switches S1 to S6. See here, we have taken the scale x-axis and y-axis 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree, 360 degree. To generate a pulses to the S1 to S6, we are following the sinusoidal pulse width modulation. So here we have taken the three sinusoidal reference voltages with a displacement of 120 degrees. This is the first sine wave. This is the second sine wave. The delay angle between the first to the second is a 120 degrees. The same manner, the delay angle between the second waveform to the third waveform, sinusoidal voltage is a 120 degrees. Now compare the three signals with a carrier signal. This is a carrier signal. Okay. How much frequency of the carrier signal we have to take it? That is depending upon the how many pulses the inverter is giving in the offside of the output voltage. Now this is the control circuit diagram. Here we have taken three comparators. One reference voltage is given to the first comparator, second reference voltage is given to the second comparator, third reference sinusoidal voltage is given to the third comparator. The same sinusoidal signal is given to the three comparators. Now here we have written the logic. If the reference is more than the carrier, then the output is activated. So the triggering circuit is giving a base voltage to the S1. The inverted voltage is given to the below divider. If it is 1, then S4 becomes off. If it is off, S4 becomes a on. Because this is a NAND gate. In that manner, we are going to generate a pulses to the S1 to S6. This is the output voltage of a PWM modulation inverter. See, in the off cycle, if you observe the width of the pulse, which is near to the 90 degrees, will be higher, and away from the 90 degrees, the width of the pulse will be lower. We are calling as a pulse width modulation inverter. The RMS output voltage of a pulse width modulation inverter is given by V equal to M into VD by 2 root 2, where M is nothing but a modulation index. It is defined as a ratio between the reference voltage to the carrier wave. Always this value will be between the 0 to the 1. By changing the modulation index, we can control the RMS output voltage given by the converter rather than controlling the VD. So these are the advantages. Harmonics are reduced, low frequency harmonics are eliminated, associated losses also will be reduced. There is a smooth motion of a machine is achieved. The machine is operated with a pulse width modulated inverter. The output voltage can be controlled by means of modulation index. No arrangement is required to get the variable DC voltage. Hence, the inverter is directly connected to the DC voltage. The harmonics in current is reduced if you use the high leakage reactance of a motor with the PWM inverter drive. Suppose if you use the induction motor with a high leakage reactance, then harmonics and current will be further decreases. So this is the PWM inverter. This directly connected to the DC voltage. This is the filter. Till we have a AC voltage. So by that time we can use the diode rectifier circuit. Is give only the constant DC voltage that we can give into the PWM. So in case of PWM inverter, you can control the output voltage by controlling the modulation index. Suppose if you want to control the frequency, that we can control by changing the frequency of a reference volt. So in that manner, you can maintain the V/F ratio in case of a PWM inverter very easily when compared to the stepper wave inverter. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel so that I am always available to answer all your